Okay, good morning everyone. Welcome to the last lecture. So let me just first finish off what we were doing in chapter 19 because we nearly got to the end, but just a couple more points that I want to make. So we'll do that, and then basically depending on what you guys want to talk about, we could do revision, or we could talk a little bit about chapter 20. I won't do so much of chapter 20, but kind of interesting, so we could do that as well. Well, let's decide after we get to the end of this. So just to recap chapter 19. So let me start on this slide where we derive the RMS root mean square velocity of an atom, and the way that we did this was by kind of trying to derive PV equals nRT, and so if you rearrange this you can see this like PV is equal to N of something something, and then so by equating that stuff there to RT we could deduce what the velocity of the atoms should be dependent on temperature. And so this is actually quite an important relation from which a lot of things in the remaining part of the chapter is actually derived. So later on when we actually figure out what the energy of a particle is, we again use that relation basically by saying, okay, so now we know the velocity, then we can use just half mv squared, and then we also know the energy. So it turns out it's a nice simple formula, 3/2 kT. And then from the kinetic energy, we can eventually work out, okay, so we did mean free path, but we did this stuff, but the point which I want to make is that from the 3/2 kT relation, we could actually work out also the internal energy of a gas. And this is something kind of new because previously we had the first law, thermodynamic first law, and we had delta E, which is the change in the internal energy, is equal to Q minus W, heat minus the work. But we never really had kind of a formula for internal energy. We just said, okay, well, here's this quantity that seems to be invariant of the path of the process that you take when you do something to a gas. But we never really had a formula for it, and now we have actually a formula for it, which we derive from a microscopic perspective. So we actually now know that internal energy is actually, has an explicit formula like this, 3/2 nRT, and it's entirely dependent on temperature. And so this is again something new that we didn't know because previously, we said, okay, well, here's all the states of a gas, and then maybe at each point there is a, internal energy, right? So, but then now because we said, oh, actually internal energy is only dependent on temperature, that actually means that any isotherm, so any constant temperature, all these states all have the same internal energy. So they're different states, but they have the same internal energy. So that's, so actually we could deduce a lot of things just from this early calculation. So from this one where, we tried to derive the velocity gave us energy, and then kinetic energy of one atom gave us internal energy over here, internal energy of the gas, and then it doesn't stop there. From the internal energy, actually we could work out the specific heat of the gas. So basically, for example, in a constant volume process, well, because we actually know what this internal energy is. This is just a definition. That's just like saying, okay, so for this many degrees, this is how much energy you need. But then now that we can relate that to the internal energy, so we worked out what the internal energy is, and then for a constant volume process, W is 0. So that means we now even can derive the specific heat, right? So there's this whole chain of derivation. So from the velocity of atom to the energy right, to the internal energy, and then now we've got specific heat, right? So all these things just followed from each other. And then so the specific heat of a gas is just given by this, and then it actually agrees pretty well with the experiment. That's pretty amazing considering, remember we were doing that calculation with a box and then the atom bouncing between the walls, it looked like pretty kind of sketchy kind of proof, if you like. But then despite that kind of sketchy proof, it actually agrees with actual things that you can really measure in the lab. This is, you take a bunch of helium and then you measure the specific heat. That's a pretty, specific, actual measurable quantity that you can actually do in the lab, and it actually really agrees, right? So that's quite a, triumph of the theory, if you like. And for constant pressure, it's Cp equals Cv plus R, and this is just because there's an extra factor of nRT from the work. And then so if you combine that and then use the fact that the internal energy is given by that 3/2 nRT formula, then we can actually also predict it for the constant pressure process. So yeah, I was drawing this table before, right? So let me kind of continue drawing that table, which sort of only half finished. So here's constant pressure. So constant, let's do constant volume first, in the same order. Get somebody to do keyboard duties. Okay, so constant volume, so this was NCV delta T, and CV is 3/2R, and then in this case work is 0, and then internal energy change is always, we can, maybe I prefer to write it in this form, nRT. So internal energy change is always basically 3/2 nRT, basically, right? Constant pressure is, this is definition, where Cp is equal to Cv plus R. And this is, nRT delta T. Because for constant pressure, it's just P times delta V. So, maybe we can write both, P delta V. And this thing is, again, always, change in temperature. 3/2 nRT. And you can see that basically CV is 3/2 R here, right? So when you do Q minus W, this will add up to this. Okay, that's constant pressure. And then so there's sort of a caveat, if you like, if you have more degrees of freedom, like so diatomic atoms, actually the specific heat is 5/2 as opposed to 3/2 because there's more degrees of freedom. The atoms can rotate, and so for each degree of freedom, there's a factor of R/2. It's sort of a rule of thumb, really, more than an actual derivation. Actual values can differ because of quantum effects. Let's not talk about that. We're going to talk about an adiabatic process. So this was the last thing that we did in the excuse me, in the last lecture. In the last lecture, and I didn't really go through the derivation, and I don't think I will today either. But there is a kind of well, on the PV diagram, the adiabatic curve looks a little bit more steep than an isotherm. So isotherms generally look like a 1 over V type of shape. An adiabatic relation follows this steeper curve where this PV along the curve is a constant. So you choose any point on on this curve, and then it's basically, it follows this relation where PV, and the V is raised to the power of Cp over Cv, which, so for a monoatomic gas, yeah, so this is monoatomic, but this one would be like 5 over 2 over 3 over 2, so 5 over 3. And what I didn't really write in this slide is, so for an adiabatic relation, by definition, the heat is 0. Okay. And in fact, we can actually have an expression for the work. I didn't really derive this in the slides, but actually we can work out the work, because if you have the work, it's integral of P and dV, right? And I've said that in an adiabatic process, this thing is the kind of the shape that it follows, and the work is basically the area under this curve, right? So basically we just want to integrate this area under the curve. And so actually we can actually do that. So for example here, the relationship for the pressure, so if imagine you're given some equation for the adiabat, and Cp over Cv, right? And this is equal to, let's call it K, because that's equal to some constant, right? So that means we have a formula for this P, okay? And so this is actually just K over Cp over Cv integral, and V initial, V final. And it's simple enough to integrate this thing. This is just, so the constant comes out, and when you integrate this, so, you know, you add a +1 to the power, Cp, V plus 1, and 1 over 1 minus Cp over Cv. Right? So you take the derivative of that, and then you get back that relation. And, well, you can substitute this, I guess, yourself, but, okay, so K over 1 minus Cp over Cv, Vf 1 minus Cp, V minus Vi 1 minus Cp of Cv. So, you know, given the shape of the curve, so you have to be given this constant, of course. This is the constant along this curve, right? But you can evaluate this thing just using the work formula. And so that's for an adiabatic relation, so we can actually work out an explicit formula for the work. And this is just always this, right? So, in fact, you know, you now have actually two quantities which should be actually equal to each other, right? So here we've got some expression in terms of the work, and we know that Q is 0 here, right? And delta E is Q minus W. So this thing here should actually just be the negative of this thing here. So it depends on what you're given, what information you're given, but you should be able to work out either this or this, depending on, well, if you're given the temperature, then you can use this. And if you're given the volume and the equation of the path there, like you need to know this constant here, but you can work it out this way too. Okay. I think I already mentioned this somewhere. An example of adiabatic processes: fast expansion of a gas, basically because the heat doesn't have time to enter. And then so the final thing here is the free expansion case. Run out of space here, but as we already said, I think in one of the earlier chapters, free expansion is a case where the heat, the work, and the internal energy change is all zero. Okay, so well, it's easy, 0, 0, 0. In fact, it's a specific example of an isothermic process because, well, if none of these things change, then well, okay, rather, sorry. If the internal energy doesn't change, then, in fact, the temperature change must actually also be zero. So basically from here you can deduce that the change in temperature is in fact zero for free expansion. Okay, so, okay, and then maybe I should just complete this table here. So I did free expansion, and then last one that's missing is constant temperature. So for constant temperature, again, this is zero, right? Because the internal energy change is zero. And we know that internal energy is just related to the temperature there. And if you remember, we also worked out a formula for the work here that was integral P to V. And that was like nRT here. I won't repeat the derivation, but it's Bf over Vi. So we have an explicit formula for the work there. And, well, I think in this case there's no such thing as a specific heat, because obviously the temperature doesn't change, right? Constant temperature means the temperature is constant, so there's no such thing as a specific heat for constant temperature because it's constant temperature. So basically the best you can do here is just to say that, well, this one, if this is zero, then this one must be the negative of that. So I think this can't do more than that, I think, in this case. So basically, we can actually fill in all of this table with actual explicit formulas basically for each one now. So, if you want to work out the heat, then, we've got explicit formulas for the, we get a F2. Hi. We get an F2, please. Okay, so we've got explicit formulas for all of these quantities, and so specific heat, we've got, we know exactly what these specific heat capacities are. Might be cut off in the camera. We've got explicit formulas here. For the work, we've got explicit formulas for basically every possible scenario. Yeah. So we've got, this is 0, this is that nRT delta T or P to V because this is constant pressure. Internal energy is always just 3 over 2 nR delta T, except for the constant temperature cases. Yeah, so basically that sort of more or less completes the whole picture for this, understanding heat and work in these processes. Okay, all right, so let's do this checkpoint here. So rank the paths 1, 2, and 3 according to the energy transferred to the gas's heat, the greatest first. I get the feeling that maybe for this one it might be easier if actually I just do it. So the way I think that you approach this one is that you do have to do a little bit of a calculation for each one, basically just following these formulas, right? So for for path 1, so path 1, what kind of process is this one? Yes, constant pressure, yeah. So for path 1, for constant pressure, so we can just look up our table here. So constant pressure, it's it's a monoatomic gas, right? So it's N times Cp delta T. So, and what's the delta T in this case? Process 1. Yes, 200. So 200. So it's N times 5 over 2R times 200. And so this is, in other words, 500 and R. Okay. Q2 is a isothermic process. So we can look at our isothermic formula. So it's basically this one. Hold on, did I put the signs right here? Oh, sorry, not minus, plus. Something wrong there, yeah. So this one, this is the formula that we have. So nRT over log of Vf over Vi. But then T here is 500, right? It's going to be 500 nR and then log of Vf over Vi. Okay. 3 is so it's supposed to be an adiabatic process. Three. Oh yeah, okay, so it says it's an adiabatic process here. Yeah, so path in this figure 3 is adiabatic, okay? And we're asked what the heat is. Well, adiabatic, it's, by definition, it's 0. Okay, so we've got now expressions for this. Now certainly Q1 and 2 are bigger than 3, right? Okay, what about Q1 and 2? Which is going to be bigger here? So basically, it's just obviously up to this log, right? So it depends on if this log factor, because otherwise it's exactly the same. This is 500 nr, this is also 500 nr. So this is like log of Vf of Vi. Now, we're not really told what, how much like bigger Vf is bigger than Vi. And the log function looks like this is x, this is log x, right? Log of 1 is 0, right? So, sorry. So it goes through here and basically goes up like that, right? It kind of depends on whether this factor is bigger than 1 or less than 1. So this one becomes 1 when this is E, right? E is 2.7. So I'm not sure if there's actually enough information there. So with the assumption that Vf is less than Vi. So if it's in this range, so Vf is less than E times Vi, right? So as long as it's in this range, then this will be the largest, this will be the second largest, this will be the third largest. But if Vf over Vi is bigger than E, so if it expands more than 2.7 times, then this would be the largest, this would be the second largest, this would be the third largest. I'm not sure if you can actually deduce something more about the Vf. There might be something deeper here, but I couldn't quite think of it. Yeah? Yeah, but I wrote that.
Oh, okay.
Yeah. Yeah, I wrote that so that there's a unique answer, but as far as I can tell just from the book, I don't know if there's you can actually deduce that fact or not. So, well, let me know if you guys figure that out. Okay, it's the end of chapter 19, the phone call. Okay, so do you want to do revision now, or you want to do a bit of chapter 20? I promise I won't do too much of chapter 20. Nobody probably wants to do more work to revise, right? But it is kind of interesting. So up to you, I guess. Well, if you don't tell me what to revise, then I guess I will just do this one. But yes?
That's revised.
Oh, right, okay. Okay, so what would you like to revise?
Important equations.
Important equations.
Yeah.
Okay, important equations. How should we do that? So, well, okay, we could just sort of flash through everything and then I could point out the things which I think are important, right? So, well, yeah, I think these things are just kind of definitions. They're less, you know, I think you're probably mainly familiar with temperature and things like this. Thermal expansion, I mean, you know, in terms of exam questions, it's possible that, you know, you might get questions, you know, I've seen questions like this, thermal expansion type of questions, but usually they're not so deep, in fact. Really, I think the main topics here in the thermodynamics is really the stuff to do with heat and work. I think if you're really going to focus on something, then you should really try and focus on those aspects. So yeah, I mean, all these things are kind of definitions. So yeah, I mean, you certainly need to know, you know, definitions of the heat in relation to specific heat and so forth. Right, and yeah, and so work done by a gas, yeah, I mean, this is definitely important. You need, this is very central to all the results that come afterwards. PV diagrams also very important. So you already saw it on the quiz. 2 questions basically in the quiz on PV diagrams. So certainly you need to get your head around those. Yeah, so these are, okay, and basically I think the main concept that you really need to understand here is that, well, firstly, the PV diagram is a map of all the states that you have of the system. And so when you're looking at various processes going, say, from 1 to 2, then what you're really doing is you're looking at the trajectory of the state of the gas, right? And so the first law of thermodynamics is important because it introduces this idea of internal energy, and that there's a kind of an intrinsic quantity that is that the gas kind of possesses, and this internal energy. At this point here, we don't really have an actual formula for it. It's just an observation that if you compare these processes, so you know, once you realize that, okay, so this is a map of actually all the states in the gas, and then you say, okay, well, I can go from state 1 to state 2 in many different ways, right? And in general, the heat and the work will be different for all those. But if you take this particular combination of the heat minus work, then that seems to be an intrinsic property of, you know, going from state 1 to state 2. And so that seems to be independent of the path that you took. It's just dependent upon the initial and the final states. Right? So definitely this is a important concept. And basically where this comes down to, this comes from is the sort of the conservation of energy. And so heat and work are really the only 2 ways that this system can actually lose or gain energy. Right? Yeah, some of you I think asked after the quiz, you know, that you were not familiar with some of these terminologies like isothermal. You know, if English is not your first language, then, you know, perhaps you need to, some of these terminologies would just be, you know, given to you in the question, and it would be just described as isothermal or adiabatic. So you really need to know what those things mean, and what they mean in a kind of rigorous sense. So adiabatic means that basically heat is 0, isothermal means the temperature is constant, constant volume means volume is constant, but so that means that the work is going to be 0. In cycles, in a PV diagram, the internal energy is the same because it returns to the same state. And free expansion, all these three things are 0. These are some examples of that. Right, yeah. Okay. And yeah. So this type of question also comes up sometimes. Composite materials. So this is not really completely connected to the rest of the chapter. It sort of feels like an add-on, I guess, because I suppose it is. But you do certainly see sometimes questions like this. So usually the question goes like, if there's, some temperature outside, inside, and there's some materials with different thermal conductivities, what is the temperature at the interface and things like this. So basically the trick is to realize that the power transfer through this is the same. And so, this formula, I believe, is not given in the formula sheet, so you should, try and, probably create a list of the formulas that you do need to remember. Most of the things which I ask you to remember are, in my opinion, fairly straightforward. So, I think with a little bit of understanding of the way that the thing works, the formula is often reasonably straightforward. So, once you understand that basically heat conduction works in the same way as a lot like electricity, so the electrical resistance. So, the thicker the wire, the more heat is transferred. The longer the wire, the less heat that would be transferred. And of course, the larger the temperature difference, this would be like the larger the voltage, right? Then the more heat that would be transferred. So basically, these things work in proportion or inversely proportional to whatever the relation is. So it's relatively straightforward. Another hint is that you can always usually the units already tell you just about what the formula should be, right? Because when you look at the dimensions of the final result, if you're trying to calculate something in power, right, like power meaning the energy per unit time, so watts is the units for that. So obviously you need to multiply by temperature here because it's watts divided by meters Kelvin, and then it's not just that you divide, you have to multiply by meters because it's per meter. You do have to remember a bit of the physical situation here because basically there's an area and a length here, right? So area divided by length has units of meters. So that's why basically this is per meter, because actually there's two length quantities that you need to multiply or divide. Okay. Yeah, these things. So some of these things are, there's less that you can really kind of do in terms from the examiner's point of view to, kind of try to make you think about the question. So, something like this is like, it's more or less, okay, here's a formula, and then you just calculate the number, and it's not that much more, there's not that much of a conceptual thing that you can really ask people to do. So these are relatively straightforward, and I think this is actually given to you in the formula sheet. So this is probably something that you need to be less concerned about, I'd say. Yeah, basic definitions like this certainly you need to know, what's a mole and so forth. PV equals nRT, definitely. Yeah, and then, but at some point I think, I don't specifically remember these formulas myself. They're not given in the formula sheet, but they're easily derived just from the basics, right? So work is integral of P and P with volume. So, this one you just get from the ideal gas. This one you get because the volume is constant. This one you get because the pressure is constant. I think this one is given to you, yeah. Probably what's more important is to realize this more global kind of connection between, okay, so from this velocity we get kinetic energy, and kinetic energy gives us internal energy. internal energy gives us specific heat, right? Yeah. This formula is, I think, given to you, so that's important. This is another one that's sort of given to you, but you do need to know what it kind of means, of course. And, well, yeah, so I think the rest we more or less covered today. Okay, so thermodynamics, I think that's mostly everything. Do you want to go through the other chapters too?
Do we have questions on chapter 20?
Well, no.
Fine.
Of course, if we didn't cover it in the lecture, then I'm not going to give it to you in the exam. But if we do something in chapter 20 today, then I might, but I mean, we're not going to cover much of it, so it's not going to be very much. So I wouldn't be scared that we're going to do more material and it's going to be like, you know, overloading you too much more. Well, okay, so let's flick through the other chapters too. So, yeah, I mean, the question in the quiz was the third one is, I mean, definitely I think that's, you know, quite a challenging type of question. So, you know, I wouldn't be too concerned if you found that difficult, because that was actually a relatively hard question. So, yeah, so potential energy, yeah, work. I mean, certainly these are pretty central types of definitions you need to know. I think, you know, getting your head around, like, sort of the details of, you know, beyond just what the formula is. So, you know, okay, work is force times distance, fine, but, you know, what does that actually mean? And, you know, there's often you say it's work done by something or work done on the system, and basically just those small words like work done by something, you know, that actually makes quite a big difference in what you need to calculate, because if there's like multiple forces, then there will be multiple you know, works being calculated, so that need to be calculated. So, for example, in that question 3, you know, there was the object, there was a spring force, there was a frictional force, and there was a constant force, right? So there were actually 3 forces acting on the same object. So you can't just say, okay, what's the work? You know, what's the work done by the force on the system? You know, there's 3 forces. So there's actually a work from the spring, from the friction, and also the constant force. In the context of that question, basically, actually, the total work was actually the important factor, right? But just to sort of understand the relationship between these things is, of course, important. Yeah, conservative, non-conservative forces, that's kind of an important concept. Yeah, so this money analogy thing is just trying to help you understand the relationship between these things. Yeah, gravitational potential energy, elastic. So certainly being able to calculate these things are more important. I don't know. So kind of everything in this chapter is pretty important, I'd say. Conservation of energy is, of course, quite central. So, you know, in this case, none of the formulas are very hard, but the concepts are more important, right? Yeah, getting from the potential energy back to the force. So this is just basically inverting that relation. Yeah, equilibrium points. Okay. these things were just a side question, so I wouldn't ask these ones in the exam. That's Gombok thing or this particular example necessarily. Right. So yeah, I think one of the confusing things in this chapter is that you start simple and you go, okay, work and potential energy, kinetic energy. Okay, simple, and then suddenly it brings in like a completely new thing. And you go, oh, I thought I knew that before, and then all of a sudden it's like, oh, now I need to change my thinking, and then that kind of introduces a new thing, and then you have to change your thinking again. So I think that maybe the confusing thing in this chapter is to be able to sort of, think sort of generally, so that you have a picture of this one that is consistent throughout. So in this case, basically, what it's sort of introducing is not just the kinetic potential energy, but essentially another source of kind of energy which might be flowing in. And essentially, the reason why this chapter is always kind of changing in terms of the statement that it's making is essentially that there's more different energy bank accounts that are being created throughout. So at first you just start with 2, and then you bring in this other external guy which has a different bank account in itself, which might be supplying all these things. And then later on, you introduce things like heat and things like that, which is actually, you can think of as another energy bank account. So this is, basically so bringing in, so we started off with just this mechanical energy, which was potential and kinetic, and then, now we can also think about thermal or even internal energy. So this is just, increasing the number of bank accounts, if you like, right? But basically, the overarching concept is still the same, that essentially there's a conservation of energy, and you can bring in more and more different energy bank accounts, but then overall the energy must be conserved, and the work is always this energy transfer between various forms of energy. For center of mass, so I think in this chapter the main concept is to use sort of center of mass, and then you realize this connection with momentum. So this is a more complicated example of the center of mass. And so essentially the center of mass can be thought of as actually kind of quite related to momentum, because basically they're all related by time derivatives, and then another time derivative on the momentum gives you actually the force, right? So this is kind of important to understand. Okay, and so relationship between force and momentum, of course that's pretty central. And then, so total momentum for many things, any objects. And then finally, eventually we'll get to conservation of momentum. Okay, and then impulse is sort of another form of momentum, but integrate the force with time. And then conservation of momentum, of course, is pretty central to this. Maybe being able to derive these elastic and inelastic collisions, this might be something to revise, because these are not given in the formula sheet, but this is kind of at the level of, by the way, I haven't written the exam and haven't seen the final exam, so I also don't know what's in there, but just from the examiner's point of view, there are types of questions which the kind of right level for you to work out an exam. You know, if we're not going to give you some super complicated integral that nobody knows how to calculate, but you know, if it's some question that's to do with just a little bit of algebraic manipulation, that's more or less at the right level, right? And the level of this calculation is kind of at that kind of level which everybody should be able to do. So, you know, first you need to know the definitions of elastic or inelastic collisions, basically conserves energy or not. And if it does conserve energy, then you can actually derive, basically by algebraic manipulation of these quantities, the final velocities of these two. And this is just algebra to get from here to here. So, you know, you might like to know the steps there. So a couple of sort of mathematical steps there that you know are used, like difference of squares. So you should be able to sort of identify the difference of squares and then perform that kind of algebra. And then manipulating these two equations, you get these two things. And then, well, yeah, applying them. Okay, so, right. Well, okay, so, yeah, I think in this kinetic energy and momentum chapters, it's a lot of the ideas are sort of conceptual, and also, I mean, problem solving is kind of a skill, so, certainly doing more problems is always going to be a useful thing for you. But yeah, I think in these ones there's not really any kind of topics that are kind of not important. I mean, like you might say it's all sort of important. In the thermodynamics one, there's clearly sort of the main theme, which is the heat and the work and the internal energy, and then there's a couple of sort of what seem like fairly disconnected subjects, like this velocity Maxwell-Boltzmann distribution, and because they're sort of disconnected, they can't be related so much to the main theme, and so that kind of maybe makes your job a bit simpler, because those disconnected subjects, I think you just there's not that much you need to kind of think deeply about. But some of these other ones where there's a lot of interconnected ideas, you need to sort of sit down and get your head around. Okay, well, yeah, and I mean the final exam will be, it's going to be more focused on the second half, because in the midterm we've actually covered a lot of the first half already, right? That's not to say there will be nothing in the first half. Definitely expect some questions in the from the first half of the course, but there will probably be more questions on the second half. Okay. Any other revision topics? Seems like you really want to do chapter 20. So. Don't worry, I won't do very much. Maybe you can just consider it sort of more just out of interest. So there's this concept of entropy and Second Law of Thermodynamics, and they're both actually pretty interesting ideas. And you might have heard of entropy, and what it actually eventually does. It's actually a measure of randomness in the system. And it's interesting that, okay, so something's random. It doesn't seem like anything that's sort of quantifiable or even measurable or something that might be relevant physically, but it turns out it actually is. And in fact, it's even related to these other things like heat and so forth. So, and the second law of thermodynamics, which probably we're not going to be able to actually get to, but eventually it uses this idea of entropy and basically says that entropy always increases if you add up all the different entropy changes, right? And so the claim is that in the universe, if you look at the entropy of the universe, it's basically always just increasing. Right? And what people say is that, well, according to the second law of thermodynamics, the entropy is basically a degree of randomness in the system. It means that the universe is heading towards a kind of a so-called heat death, where it just gets more and more disordered and just gets disordered, and essentially at the end it's just complete disorder. And so basically we're heading from some state of order to complete disorder, right? And at that point, basically, there must be no kind of structure to anything. So, okay. Well, so let me start here. So, in the first law, what we saw was that there was a particular quantity, Q minus W, which was kind of independent of the path, right? So we've already sort of said that. And this was kind of something intrinsic to the initial and final state. This is why it didn't depend upon the path, because there's some intrinsic property at the beginning and then of the gas, and then there's some property at the end. And then, it doesn't matter how you got from point A to B. If you calculate the change in that, you will always get the same answer. So, that was the interesting observation of the first law. Now, it turns out that there's another quantity that people were a bit surprised about. And it's also independent on the path. So it doesn't matter what path you took, A, B, or C, and then you'll always get the same answer, right? And the form of this thing is a bit weird. So it looks something like this: integral of dq over t. This is basically our first definition of entropy, okay? Eventually we're going to connect it to that, disorder, and, well, I don't, maybe in the last 15 minutes we won't, but eventually this will, be connected to a measure of disorder. But at this level, just think of it like, guys in the 18th or 19th century playing with gases and then measuring the heat and doing stuff like that, right? And then they, mapping out the states of a gas like this, and then they hit upon a new kind of quantity, which also seems to be independent on the path. So this formula is a bit weird. I mean, when I first saw it, I was also a bit confused. I think I didn't understand it very well when I was in first year physics. I think what I was confused about was what is this integral here? What are we integrating over, and what's this temperature, and why am I integrating over the heat, right? So let's just say, let me just describe what this integral actually means first, right? So basically, we're going from one state to another state of the gas, they have different pressure, volume, temperatures, right? And then what you do is you say, okay, well, let's go along path A first, okay? So what we're going to do is we're going to move it a little bit, so the pressure and volume temperature is a bit different. And then we're only going to move it a tiny bit because what we want to do is we want to look at a process where the temperature doesn't change so much, okay? So the temperature here and here is like basically the same, okay? That's the temperature that we're going to use, okay? Or here maybe. Okay, and then when we go from this one to just slightly along path A, some heat might go in or out, right? So we measure that heat, okay? And then we keep on doing that. So we chop this into another piece, going from just a little bit here to over here. And then that will have maybe slightly different temperature, so I've called it T2. And some heat will go in or out of the gas. And then we keep on doing that until we finally get all the way here, okay? So we add all the little bits of heat that have gone in or out of the gas, and we divide by the temperature each time. Pretty weird thing to do. I don't know how you even think of looking at that as a quantity, because there's no hint of like anything like, it's not very intuitive. Like why would you divide the amount of heat that goes in or out by the temperature? It's sort of, are we doing something like this, or it's not very intuitive. So if you're confused by it, then I guess you're in good company, right? Okay, and then so basically the point that is being made is that, okay, if you calculate that particular thing along various different paths, A, B, or C, then you'll get the same number regardless of which process or which path you took, okay? So that's pretty curious. That's the general case. Now, actually, for isothermal process, the calculation is much easier. Is because the reason why this was a bit hard to calculate is because along this path, the temperature might be changing. Because this is not necessarily an isotherm curve, right? So maybe C is certainly not. Doesn't. Isotherm should look something like this. C is this way, right? So temperature might be changing this whole time, right? So the temperature is dependent upon which point in this path you are. So that's why this integral is a bit hard to calculate. But for isothermal process, this change in entropy that we dq over T. So because it's an isotherm, the temperature along this path is always the same, right? So actually this temperature can come out of the integral. And then we just have to add all the heat elements that go in or out each time you go along the path. And then so that's just the total heat, right? So for isothermal process, this integral is easy to calculate. So it's just the total heat that's gone in or out, and then you just divide by the temperature, right? So, that's just evaluating it. Doesn't tell you anything about what it is, or just an experimental observation that this quantity is actually a path-independent process. Okay. All right. So, well, given that, let's look at this. So, water is heated on a stove. Rank the entropy change of the water as its temperature rises from 20 to 30 degrees 30 to 35, or 80 to 85. So which one would be the biggest? So let's look at this formula. So the change in entropy is, well, if we don't worry so much about the integral, it's something like heat over temperature. Okay. So if we want this to be big, we obviously want the heat that's gone into the system to be large, but we also want the temperature. And this is not change in temperature, this is just temperature. Okay? So we want the temperature of the system roughly. It's actually going up in these cases, but we want it to be small, right? So if you look at A, well, in terms of the heat that goes into it, well, heat, we know it's just like specific heat of the water, and then times by the whatever your temperature difference is, right? So the largest temperature difference here is this one, right? It's 10 degrees change. These ones change only by 5. So this one has certainly the largest heat input, right? Because the temperature change is largest. So A would be the largest in terms of the heat. But actually it's also the smallest in terms of, well, actually the temperature is changing, so we really should be doing integral, but let's just be approximate here. Now, this thing, and by the way, we need to do this in Kelvin, not degrees, so if you put 0 degrees Celsius, this will blow up, it doesn't make sense. So, in Kelvin, you put that in Kelvin, but it doesn't matter if it's Kelvin or Celsius, the lowest temperature is the lowest. So, this T here is on average like pretty low. So this has the largest Q, but then also the smallest T on average. So this has to be the largest entropy change. Okay. Both of these ones have 5 degrees change, so the heat would be the same. But then the temperature, or the average temperature, would be different. So which one would be the second largest? B, right, yes, because that's got the lower average temperature of the two, right? And this is Q divided by T, so the smaller the T, the larger this thing is. So it's going to be A, B, and C. And in fact, you can actually work out a formula for the entropy because, okay, for an ideal gas. Oh yeah, sorry.
Why do we put average temperature?
Yeah, so because you're right that really should be integrating. The temperature is actually changing in this process, right? But approximately, basically, I'm saying this integral is approximately 1 over T average times Q. Okay, that's basically what I'm saying. Q over T average. Because what I really should be doing is looking at the heat that went in at each, say you heat it up a tiny bit, say you start at 20 degrees here, right? Start at 20 degrees, heat it up a tiny bit, okay, it goes 21 degrees, right? And then I put in T's, like maybe 20.5 or something. And then measure the heat that goes from 21 to 22, and then divide by, this time, like 21 or something. And then I should repeat it. That's the proper way to do it, right? But just, roughly speaking, that is probably not going to be so different as an answer as if I just put in, say, 1/25 here, right? Because, okay, what I should have been doing is putting in the real temperature, so I'm approximating 25 degrees by 2030, right? It's not going to be so different. So, yeah, it's an approximation, but that's what it is. Okay, so, well, I've only got a few minutes, so let me just sort of maybe give you a taste of what the big deal of this is. Okay, so for ideal gas, you can actually evaluate it, and indeed you can see that it's a state function. But yeah, it's still, well, okay. And then later on, basically, you can show that it's actually related to some microscopic perspective. So probably the most amazing thing in this chapter is that you can actually relate this thing to a microscopic calculation of the entropy. And this is, I think this is Boltzmann. It's his grave. He's got this formula for entropy on his grave. And you can actually work out that this thing, which seems a pretty weird thing to calculate, what it's actually doing is it's actually calculating something like the log of the number of different microscopic configurations of the gas. So it's actually really a measure of the randomness of the gas. And eventually what this kind of culminates to is that you can show that any entropy, any process actually is always increasing in entropy, going from some state of order to disorder. It's a state of super disorder. And yeah, and then there's a second law of thermodynamics that says that basically this thing always increases. Okay, but in terms of the exam, I'd say, okay, we got up to this point, I guess, here. Okay, so this is the last slide for the purpose of the exam. Okay, so that's it. Well, I hope you learned something from the course. It was very enjoyable teaching you all. And oh yeah, and don't forget to hand in the assignment write-ups today. So, as I said, you can hand them in by paper copy or electronically anytime today. And best of luck for the exam. Okay.